So, that's my exciting. Do you guys have exciting? Not that exciting. I don't know. Okay, for some reason it's really exciting. Okay, we gotta get going here. Enough. Yeah, anyway. I can talk all day about cool hardware for deep learning. Let's get started. So we'll start with prayer. Invite us. And one, two.
We're so very grateful for this day. We're grateful, Father, to be here on campus to learn a little bit more about intellectual intelligence. Pray, Father, that as we work through and last week, many of us can understand applying to class. Thank you very much, Father. We say these things in the name of Jesus Christ.
Yeah, we're gonna basically spend all day talking about the lab and PPO. So I'm gonna give you hopefully lots of support to help you out. But first, it's Monday. I have a thought for you. This is a scripture and a video. I usually don't do videos, but it's my old mission scriptures. Been around for a while. So I caught this video just the other day. And I wanted to read you this scripture. I think any time there's a commandment that's repeated twice, you should pay attention. It's 3 Nephi 11:37-38. And again I say unto you, you must repent and become as a little child, and be baptized in my name, or ye can in no wise receive these things. And again I say unto you, you must repent and be baptized in my name, and become as a little child, or ye can in no wise inherit the kingdom of God. And I thought, yeah, okay, so it's not just a good idea to become a little child, it's actually a commandment. So think about that. You're commanded to become like a little child. And I was thinking about that, I think there's lots of ways to do that. I think they're humble, they accept correction. We're constantly correcting our kids. If I did that to any adult, they'd punch me. But we're constantly telling them how they can improve their life. They're humble, they accept correction, they listen, they obey mostly, but they also oh, be careful. I also, okay, this goes on for like 10 minutes. Okay, you get the idea. I don't know, I could watch this all day. So I thought, yeah, they're humble, they accept correction. They're also creative. I wouldn't have thought to use a broom to help push the little baby along on her little cart, and they find a certain joy and happiness in life, in simplicity, and a certain joy in innocence and just having a good time. And I thought, it's a dimension of becoming like a little child that I hope I can find more of in my life. Just taking joy and pleasure in simple and wonderful and uplifting things, and being creative. And like, nobody asked my kids to do this. They weren't in charge of the baby. They just somehow decided it would be a lot of fun and wonderful to play this little game with her. And they did. And I thought, that is, it melts my heart. And I'm like really thankful that my kids just do good things like that, just spontaneously. And I thought, I want to be more like them. I want to be more like that. And I thought I would like to share that with you, that I hope you all can. You're all so busy growing up, you're all busy being adults, but you're also commanded to be like children. And so I invite you to think about how you can do that in your own lives. In the name of Jesus Christ, amen. There's another video I've got to show this another time. When Evie learned to play the recorder. Yeah, it's noisy. I don't know who invented the recorder, but I'm not happy with that. Okay, let's talk about proximal policy optimization. So, this is the lab for this week. So you're to implement PPO. We'll be talking about it on Friday. We'll talk about it some more today. We ran out of time on our video. We'll continue that. But first, I thought, okay, let's do this. I want to make this as easy as possible for you to implement, but I want you to have fun and do some interesting things while you implement it. So I've revised the spec a little bit this morning. If you looked at it earlier, take a look at it now. It's basically the same, but I've added more detail. Okay? So for this lab, you're just going to implement proximal policy optimization. Now, the caveat is, this is, what I'm trying to do is trying to turn these lab assignments into things that feel more and more like your final exam. I mean, like your final project, sorry. Hard stuff. Final project. So you're going to implement the PBO algorithm. You can use any code that you want from the internet to help inspire you and to see how other people do it, but all of your final code must be your own, okay? I know that's like a fine, tricky line, but essentially like no cutting and pasting. And we're going to go over some code today to help you understand how to implement it, how to set it all up. Yeah. You can use the word code, of course. I mean, it's not there. A lot of these people take a supplement. Yeah.
Where would you recommend we find other code or other examples? Do you have any suggestions for that? For those of us that are
The video points you to
Just go to google.com. I'm sorry, that's, yeah, sure.
So just Google it.
You can Google it. So if you Google PyTorch PBO, you'll find some stuff. But yes, in the video, they take you to, I think it's called like RL Adventure -2. And they have RL implementations of several things. There is a PPO implementation here, which you're welcome to check out. And it's pretty good. I think it's pretty clean. So you definitely start that. Oh, and the code we'll go over is a lot like that. And maybe we'll just go over this code. Okay, so you're going to implement that. You can use any code. But what I want you to do is I want you to do a little bit of science with this lab. So you have to implement it on what's called the cart pole problem, which is a very simple two-dimensional state space. You're a little cart. I remember this important. You're a little cart on a linear track. You have a little pendulum, and you can move the cart backwards and forward. You just balance the pendulum. So there's like two actions, left or right, and you just get a reward if the thing is balanced. And if it falls over irrecoverably, then the episode terminates and you get a negative something reward. Okay, so you have to implement PBO on that domain. But then you're also required to implement it on at least one other domain. So one other domain can be anything that you choose. So I recommend choosing something interesting. It could be like a little robot problem, it could be a little video game problem, it could be whatever you'd like. The reason I'm asking you to do this in OpenAI Gym is because if you set up your code, so OpenAI Gym, for those of you that don't know it, is just a suite of reinforcement learning control problems with a standardized API. So all you have to do is you import Gym, kind of looks like this, and then you say gym.make, and you give it an environment name. And that gives you this environment, which you can then reset, you can interrogate and ask, what's your state space like, what's your action space like, and you can step in the environment. So you give it an action, you call step, it gives you back a reward and an observation. You do your thing with your neural net, get some new actions, hand it to Jim, and you keep going. But the fact that it's a unified API means if you've coded everything correctly, then probably all you'll have to do in order to implement the second domain is change this string to whatever other Gym support domain you'd like. Okay? So you implement it using OpenAI Gym, implement Cartpole, and most of the example code that you'll see out on the internet typically will implement Cartpole. So to do this, here's what you have to do. So implement a policy network. So what is policy network going to look like? Mapping from, says it the board, states to actions. Okay, so you just got some neural net, and you've got a state that's going to come in. It's going to go through some number of layers, and then a distribution over actions is going to come out. If they're continuous actions, you'll probably need a little Gaussian. If they're discrete actions, you'll just need a little multinomial. Okay, and then a value network. So this is just a mapping from states to the value of that state. So the input has what size? What's the size of the input to this network? Sorry? 5? Always? Okay, so it's, this is a mapping from states to action, so this gives me 4. In the case of Cartpole, so probably 4 comes in, and how many come out? 1. Just 1, because it's just the value of the state. Okay, a loss function for the value network. So we want to compare the actual return to the expected return. What is the obvious, and they're both scalars, so what's the obvious way to compare them? The simplest possible thing? Mean squared error. In this case, this would be like square error. The PPO loss function. This is the trick of the lab. Okay, this is what we're going to spend some time going over. And then you're just going to train these. And you're going to train them by generating data. So you're going to generate rollouts. So you're going to use the simulator, the GIM simulator, policy network. You start with some initial state. You ask, what's my policy in that state? It gives you an action. You feed that into GIM. It takes you to your next state. You say, what's my policy for this state? It gives you an action. Feed it into GIM. You roll out until you either get some length of time or you terminate. And you call that one rollout. You do that a bunch of times, generate a bunch of data, and then for each rollout, you're going to calculate the actual sum of discounted rewards that you observe along that rollout. So that's really easy because you just iterate over all the rewards you saw and count them up. Then you're going to use that as training data to train the value network. We'll talk a little bit about, again, how that works. So you take the value network, and its job is to estimate the value of the state. Well, this is a supervised learning problem, because here we have a bunch of states, and we have the actual value for them. And then using the actual and estimated value to calculate the advantages, and then using those advantages, we can implement the PPO loss function will train the policy network. Okay? So that's the rhythm of this lab. So like I said, there's quite a few moving parts, but because you're allowed to use any code on the internet to help you, it shouldn't be too bad. What I want you to do, though, is show me that your code is working somehow. So that's sort of this 30%. You need to implement PPO on your whatever domain you'd like, but then show me that it's working. And that may vary depending on which domain you pick. And there's a discussion of this in the spec. So probably the obvious thing to do is just show reward over time. And it should go up as your policy improves. But it could also be things like the number of steps until the pendulum, like the cart pole thing, the pole falls over. That should also go up over time as your policy improves. But you can show me a video of like your cool agent running through the maze, or you can show me some like dollars as your stock trading agent like makes money, or whatever you think is appropriate. Okay, so question. So now that you've got kind of the outline, we're going to start learning the details of the PPO algorithm. We're going to go through some example code, the paper, and the video.
Out of curiosity, will like the GIM video, is that thing working in the lab?
No, no. Okay.
Sure, network, so from one domain to another, should we worry about changing the networks or whatever? Because sometimes you could throw in like an LSTM to help with like remember stuff over time. Should we worry about that? Or?
I would not, if you don't have to. So first of all, if your environment is fully observed, there's actually no reason to remember anything because state is a sufficient statistic. So you're good. It's only in partially observed domains where you might want to remember something. So the definition of a partially observed domain in this case is really simple. It's just, if I show you a screenshot, does that uniquely identify where you are? And the answer is in some domains, yes, but in some domains, no. So for example, in the little maze world, there's places in the maze where the pixels look exactly the same, but you're in two different places. And that's why you might need something like an LSTM to help you remember. But in something like Space Invaders, like we talked about, you show me 2 screenshots, and it's fully disambiguous. Okay, keep going.
Where does the gradient appear in this?
When you train the value network, you'll be taking the gradient of the PPO loss function. Do that. So we'll talk about that in just a minute. Okay, so here's like a little bit of scaffolding code that we were using. It's not even scaffolding code, it's just sort of showing you how we structure it. So we have a policy network, which you all know how to implement. And I think we use a very simple network. I'll actually show you the code in just a minute. And a value network. We set up some data sets just to help us keep track of things. And then the basic loop looked like this. So we had a little bit of initialization here. Make our domain, make our networks, set up 2 optimizers, one for the policy and one for the value. And then our hyperparameters are, we're going to run 1,000 epochs. For each one, we're going to grab some samples. The episodes will be at most 200 steps long. This is our discount factor, etc. So then this is the main logic. So
Quick one, Gabe?
Yes.
What's an episode, sorry?
An episode in this case is just a rollout.
Okay.
Rollout episode. So we first generate a bunch of rollouts. Then we approximate the value function. Oh, sorry, we calculate the returns of the rollouts. Then we approximate the value function, so we train the value network for a couple of steps. And then we calculate the advantages using the trained value function. And then we train the policy network using the PPO loss function. Okay, so now that you kind of see how this is all going to fit together, we're going to watch that video that we didn't quite finish. He's going to be explaining the loss function to us. Hopefully now you sort of know where we're going. The video is going to make more sense. Okay, but any questions before we dive in? I also Googled how to change the playback speed in QuickTime. And now I know you use the option key. I was using the command. So I think we just got to the seal, past the seal slapping, right? So if you press play.
So first, let's define a variable R theta, which is just the probability ratio between the new updated policy output and the output of the previous old version of the policy. So give
Can you guys hear that? A lot.
is exactly what PPO does. Okay, so now that we have a little bit of surroundings, let's dive into the crux of the algorithm, the central optimization objective behind PPO. Hold on to your hats, it's about to get a little technical. So first, let's define a variable R theta, which is just the probability ratio between the new updated policy outputs and the outputs of the previous old version of the policy network.
So why do we do that? Because remember the discussion over here? Anytime you see the ratio of two probabilities, what are you supposed to think? Monte Carlo? Yes. Important sampling. Important sampling. So we've got data which was sampled under an old policy, and we're going to want to somehow reason about it under a new policy. So that's what R theta is helping us to do. It's telling us how to compensate for the fact that we're changing policies.
So given a sequence of sampled actions and states, this R theta value will be larger than 1 if the action is more likely now than it was in the old version of the policy. And it will be somewhere between 0 and 1 if the action is less likely now than it was before the last gradient step. And then if we multiply this ratio R theta with the advantage function, we get the normal TRPO objective in a more readable form. And with this notation, we can finally write down the central objective function that is used in PPO. Here it is. Looks surprisingly simple, right?
Okay. Let's talk about this. So the loss is a function of theta. This is our policy parameter. So let's see if we can unpack this, and then he'll explain it. Okay, so what is this over here? Expectation over time. We'll talk about that in a second. So we're taking the min of what? Yeah, so let's see if we can take the min of this thing, comma, this thing. Okay? Okay? So what is this right here? That's the, okay, so RT is not reward. What is it?
Ratio.
The ratio. It's that ratio we just talked about. So at time t, we'd like to know what the ratio was of a particular rollout under the old policy and the new policy. That's this guy. And then we multiply by what's a hat t? And the advantage, which is positive if it was an extra good rollout, and it's negative if it was an extra bad rollout. Why is there a little hat here? Approximate, right? So the approximate advantage function. Okay, clip. What do you suppose that does? Clips something. So what is that? What's it going to do?
The trust region.
Yeah, okay, so good. So this is, so clip, if we just were to guess, what do you guess that clip does? 1 minus epsilon and 1 plus epsilon here, and the ratio thing here. So remember, if the policies are identical, what's the ratio? 1. So probably, and actually this is not probably, this is actually true, but if we, I think we'd even just guess and get it right. Clipping this thing, we're saying, if you're higher than 1, what does this get clipped to? Or, sorry, yeah. If it's more than 1 plus epsilon, it's going to be clipped to epsilon, 1 plus epsilon. If it's less than 1 minus epsilon, it gets clipped to 1 minus epsilon. Okay.
I have a question about R actually.
Yeah.
So before we were looking at the ratio, it was like the policy of some action given some state. So does this R go over all actions?
Okay, so this R, my understanding, this is what we implemented, is that this R is actually at each time step. So the reason this is an expectation over time is that we think about every time step. Let me just make a little figure here would help. We imagine that there's some initial state, and we're doing all these rollouts. And we think about an expected value at time t, thinking about all of the data this way. And so we can calculate the different state. We know the different states here, and we know what our estimate of the value was, and we know what the advantage is at each time step.
Okay.
And so
that ratio was originally, it was like pi, it was the probability pi some action, yeah. So it's,
Right.
the ratio has this action and state.
Right.
So is that for the action and state at time t?
yes.
Okay.
So at time t, there was some specific action which was taken. Sorry, on this rollout.
Right.
You were at some state, that's st. You took some action that was at, and you got some reward, which is rt, but not the rt ratio.
Right.
Okay, so then we ask, what was the probability of that action in that state under the current policy we're thinking about, and the old policy that we did the sample under?
Right. And then, okay.
Okay? So we're gonna be averaging this way. Okay.
And with this notation, we can finally write down the central objective function that is used in PPO. Here it is.
Okay, so whoever said this is the trust region is exactly right. So we're saying what we don't want is we don't want this ratio to be too big. If it's too big or too small, that means that our policies are so far apart that this is going to be garbage. And so we're constructing a trust region that's epsilon to epsilon y. Okay, and then notice that this clipped R is multiplied by the advantage. So it's a little bit funny because we're taking the min of the ratio times the advantage and the clipped ratio times the advantage. And he's going to explain the intuition for why that is.
Looks surprisingly simple, right? Well, first of all, you can see that the objective function that PPO optimizes is an expectation operator. So this means that we're going to compute this over batches of trajectories. And this expectation operator is taken over the minimum of 2 terms. The first of these terms is r theta times the advantage estimate. So this is the default objective for normal policy gradients, which pushes the policy towards actions that yield a high positive advantage over the baseline. Now the second term is very similar to the first one, except that it contains a truncated version of this r theta ratio by applying a clipping operation between 1 minus epsilon and 1 plus epsilon, where epsilon is usually something like 0.2. And then lastly, the min operator is applied to the 2 terms to get the final result. And while this function looks rather simple at first sight, fully appreciating all the subtleties at work here takes a little bit more effort. So bear with me here, I promise we're almost there. Firstly, it's important to note that the advantage estimate can be both positive and negative, and this changes the effect of the min operator. Here is a plot of the objective function for both positive and negative values of the advantage estimate. So on the left half of the diagram, where the advantage function is positive, are all the cases where the selective action had a better than expected effect on the outcome.
Okay, so let's think about this for a second. So is the RT sub theta, is that ever negative? No, because the ratio of two probabilities is positive, so it's always going to be a positive number. So the only time we can get something negative in this clipping thing is when the advantage is negative. So those are the two cases. There are cases where the advantage is better than expected, and there are cases where the advantage is less than expected. So those are the two halves. And then this is what the function with the min and the clipping stuff is doing. So he's going to explain that why.
And on the right half of the diagram, we can find situations where the action had an estimated negative effect on the outcome. Now, on the left side, notice how the loss function flattens out when r gets too high. And this happens when the action is a lot more likely under the current policy than it was under the old policy. And in this case, we don't want to overdo the action update too much, and so the objective function gets clipped here to limit the effect of the gradient update. And then on the right side, where the action had an estimated negative value, the objective flattens when r goes near 0. And this corresponds to actions that are much less likely now than in the old policy, and will have the same effect of not overdoing a similar update, which might otherwise reduce these action probabilities to 0. Remember, the advantage function is noisy, so we don't want to destroy a policy based on a single estimate. And finally, what about the very right-hand side? Well, the objective function only ends up in this region when the last gradient step made the selected action a lot more probable, so r is big, while also making our policy worse since the advantage is negative here. And if that's the case, then we would really want to undo the last gradient step. And it just so happens that the objective function in PPO allows us to do this. The function is negative here, so the gradient will tell us to walk the other direction and make the action less probable by an amount proportional to how much we screwed it up in the first place. And also notice that this is the only region where the unclipped part of the objective function has a lower value than the clipped version, and thus gets returned by the minimization operator. Pretty clever, right? And if you're wondering how on earth the authors from the PPO paper managed to design this specific reward function, well, it's quite likely that they had an intuitive idea of what they wanted the objective function to do. So they probably sketched a bunch of diagrams that satisfied the behavior that we just discussed, and then came up with the exact objective function to make it all work out. And don't worry if you didn't fully get all the little details involved. Basically, the PPO objective does the same as the TRPO objective in that it forces the policy updates to be conservative if they move very far away from the current policy. The only difference is that PPO does this with a very simple objective function that doesn't require to calculate all these additional constraints or KL divergences. And in fact, it turns out that the simple PPO objective function often outperforms the more complicated variant that we have in TRPO.
So by the way, these are some great domains to test on. All right. These are some great domains from the OpenAI Div to test on. So these are all relatively low-dimensional control, low dimensions of states, evident actions, control problems. So, and they come with fun visualizations, so you can make little movies pretty easily with them. So the cheetah we've seen actually before, it's a little, literally like half a cheetah, a little dog-like thing, kind of trying to run along. So you get reward as you're able to move forward. Hopper is a one-legged thing, just like hops along. Same sort of thing you get reward for moving forward. Double inverted pendulum is you're balancing a broomstick on top of a broomstick. That's a tough one. And then reacher is the thing where you have to move your arm and grab stuff. Swimmer is this little, like a little underwater thing. And the two-dimensional walker, I think, is like a humanoidish thing. So these are all great problems to test on if you want one.
Simplicity often wins. All right, nice. Now that we've seen the central objective function behind PPO, let's take a look at the entire algorithm end to end. So as mentioned before, there are two alternating threads in PPO. In the first one, the current policy is interacting with the environment, generating episode sequences for which we immediately calculate the advantage function using our fitted baseline estimate for the state values. And then every so many episodes, a second thread is going to collect all that experience and run gradient descent on the policy network using the clipped PPO objective.
Okay, so this is your main loop, right? And we saw this a little bit in the pseudocode. Yeah.
So that ratio, we have pi theta and pi theta old. So the pi theta old is whatever we were running with.
Right, it's the behavior policy.
So what is the new pi theta? Because we haven't updated, right? We're
So
computing
here,
this behavior.
Right, so notice up here, right, you're running the policy, so it might have been clear to call this theta behavior. So high old is whatever you were using to actually collect the data.
Correct.
But then notice that down here, when we start optimizing the policy network, pi changes.
Oh, because you're updating multiple steps.
'Cause you're updating
This
multiple
is a single
steps.
step right there.
Right.
Okay.
So you're taking multiple steps, so the policy is changing and it's diverging, it's getting farther and farther away from that behavior policy. And so, but we want to use the data that we collected here in this optimization loop here, and that's why we need that ratio. Good, good question. Yes?
And when it says optimize circuit L, the L is a maximization in this case, right? So we're trying to maximize the
Yes, in this case.
probability of.
We're trying to maximize the value of the policy.
Right.
You can also minimize the, if you feel more comfortable with that.
So the intuition we're trying to do here is that we have this agent that's kind of doing stuff, and we kind of, it does all these actions, and it tells us to do all these actions, and then you say, all right, now run all these actions, find what rewards you're gonna get, and then optimize based on those rewards, and then go again, as kind of this back
Yeah,
and forth.
yeah, so.
Play around, give rewards, play around, give rewards.
Yep, so we run under pi old, we get a bunch of these. For each one, we have all the rewards along here, so we can calculate the actual return at every time step. Then we can also, if we have a value function, which maps states. Here, you guys awake back there? Curtis? Sorry. Thanks for taking the GoPro. You guys can throw that away for me, that'd be great. Okay, so we roll it out. So we got the actual return. For every point along the state, we know what the estimated value of that is. So we can calculate the advantage, which is just the actual minus the estimated. And then what we want to do, so the objective function is saying, try to make things where the advantage was high, make that more likely. And try to make things where the advantage was low, make those less likely. So we want some of these trajectories. So if this was a higher, and this one was higher, and this one was higher, we want these trajectories to be more likely, and we want these trajectories to be less likely. And so we collect the data here, we compute the advantage estimates. So in order to compute the advantages, we have to ask for what the value is of each state, and then compare that to the actual return. Yes?
And so are we optimizing the value network in between the run policy line and the computer
Yes.
lines?
Yes, sorry, that's not, I guess that's not shown here, but yes, so in our code what we did was we ran for a little while, and then right here we trained the value network for a little while, and then we trained the policy network for a little while.
Oh, so you train the value network after you computed the advantages of the whole value network?
Let's see,
Like, are you updating the value network right before you compute advantage, or are you doing it after the load?
yeah, so we actually, that's right, we actually computed the advantages after we had updated the value network.
Oh.
Yeah, so I'm not sure why they did it that way here, but it probably doesn't matter so much.
Yeah, order.
Yeah, I don't think it's a big deal.
And as was done in training the OpenAI 5 system, these two threads can actually be decoupled from each other by using
If you implement it this way, let me know and you get bonus points, okay? So this is like some crazy real-time, super distributed, really hard to decode out, but awesome when it's done, sort of thing.
of remote workers that interact with the environment using a recent copy.
And if you have access to 500 CPUs to implement this, let me know. Or 2,500 CPUs.
How many CPUs does that NVIDIA thing
It's
have?
only got 96.
Not enough.
I know.
Of the policy network and a GPU cluster that runs gradient descent on the network weights using the collected experience from those workers. Note that in this case, each worker has to refresh its local copy of the policy network pretty often to make sure that it's always running with the latest version of the policy network to keep everything nicely balanced. Now importantly, the final loss function that is used to train an agent is the sum of this clipped PPO objective that we just saw, plus 2 additional terms. The first additional term of the loss function is basically in charge of updating the baseline network.
And this is, because these are linearly combined, if your value network and your policy network don't share parameters, which is entirely possible, and it's probably the way you should start. Then when you take the gradient, when you train to here, so essentially if your policy network depends only on, so the PPO loss function depends on the policy network, the value function depends on the value network. These have separate parameters. Then when you take the gradients of one versus the other, you're essentially training one network to the other independently. That's what we do. But you can't have those networks share parameters. The reason that's useful, by the way, if you think about, so both of these are mappings from states to something. And so you can sort of imagine that your policy network, which is a mapping from states to actions, and your value network might have similar kinds of pre-processing. So imagine that you're doing something with pixels. Those pixels could come in, they could go through some low-level layers, some convolution stuff, extract a bunch of features, and then those features might be useful for predicting actions or values. So you can totally construct a single unified network. But to keep it simple, you don't have to.
Objective that we just saw, plus 2 additional terms. The first additional term of the loss function is basically in charge of.
Actually, I think we need to stop there because so you can all finish watching this on your own. What I want to do now is to take you through our code. So I'm going to take you through the reference code that we put together, and just see if you have any questions about it. So we're not going to post this, but like I said, you can use any code you want on the internet, and it should be similar. Okay, so let's dive in. So our policy network was very simple. So this is going to be, for the cart poll, it's going to be a mapping from 4-dimensional input to a 2-dimensional output. We parameterize it with state dimension and action dimension. So we have linear value, linear value, linear value, and then just linear on the output. But then notice that the final one is softmax. Okay, so what that does is it takes a state as an input and outputs a probability over whatever the state dimension was. So it's going to give us a probability of some actions. And then, let's do it like this. Yes. Okay. Then forward and backward, it's all the same. Okay, so our value network, similar. So it's going to accept as input a state, and I'm using a scalar, which is the value of that state. So we've got so it's got linear value, linear value, linear value. Notice that it ends with linear, but no value. Why? Values can be positive or negative, so we want to make sure we don't have some crazy, weird positive only thing on output. Okay, and a simple advantage data set which collects the advantages. Simple policy data set which collects, these both collect vertical allows. This is pretty straightforward. I mean, you don't have to learn it this way. So calculate returns and calculate trajectories. So calculate returns, the job of this function is I give you a set of trajectories, and for each one, I want to know what is the actual return along that trajectory. So all we're going to do is we're going to add up all of the rewards, and we're just going to discount them by gamma. It does it backwards. Why does it do it backwards? It's just a clever little math trick.
Why does it do it backwards?
Mm-hmm. So it starts at the end and it works
I
forward.
just would think it would be the way that it depends on the list, so the ones at the end would be the, if you keep multiplying by gamma, you're exponentially
Right.
growing.
So notice this current reward is what it's accumulated so far, working its way backwards. So it's going to, as you multiply by gamma every time, it'll be doing a proper discounting. So this just saves you the extra work of having to exponentiate gamma at every version.
So the term returns is value.
So the return, okay, so the difference between return and value is the expected reward. A return is the actual reward that you saw. So that's why this code is literally just summing up rewards. So then advantages is the difference between those two things. So for the advantages, for each trajectory, we just ask our value network, hey, what's your estimate of the value of this being in this state? And then we calculate the actual return from that point. and we go ahead and calculate the difference, and that's the advantage.
The difference between what actually happened.
And what we expected to happen. Right. Okay, so then our main is very simple. So we construct our environment, we construct policy and value networks, policy and value optimizers. Our value criteria is just MSE loss, so this is just comparing what we actually expected, and sorry, for the advantages. And then these are the hyperparameters, which are in the lab spec that we use. So here's our code, our main code. Yeah.
So I noticed in the ad you have weight decay.
Yes.
How have we done it before? Is
Oh.
there- what is that? What's the purpose of weight decay?
I think, so I actually don't know why, so actually it was Josh Greaves who implemented this for me, one of the students in my lab. So I think the reason he did that was probably because the policy is non-stationary. And so what you don't want is you don't want all of like the learning rates and everything to go super low as over time. So my guess is that this is just helping